Okay, let's go ahead and get started. Welcome everyone to our GIA Knowledge Sessions. These are a series of talks and seminars about gemology that are fueled by our decades of research. And, it's our mission to share all of our discoveries and learnings with the world. So I'm really excited to kick things off today. I'm Kelly Giordano, a member of the content team here at GIA. And I'm joined by Dr. Ulrika D'Haenens-Johansson, a senior manager of diamond research at GIA, and she's going to tell us all about glowing diamonds. So before we get started, we'll have just a bit of housekeeping here. Everyone attending this is automatically muted. If you have a question, please submit it using the Q&A feature at the bottom of your screen. Feel free to ask questions as we go, and there will be a Q&A session at the end where Ulrika will have the opportunity to answer some of your questions. Later today or early tomorrow morning, we'll also send a recording of this session along with a survey, so we would love to hear your feedback. And with that, I'm going to pass you over to Ulrika.
Hi everyone. So today I'm going to be reviewing some of the fascinating features that we're able to observe with diamonds through fluorescence and cathodoluminescence techniques. In particular, we'll be looking at the formation of growth structures and the defects responsible for these very, very beautiful features. So when one thinks of diamond, a lot of people think of it as being a perfect material. But the truth of the matter is that diamond is not perfect. Diamond consists of carbon in a tetrahedral arrangement, as shown here to the left. So where each one of these little gray spheres is a carbon atom. And this system, this lattice, actually contains a lot of different imperfections. So these imperfections that I'm talking about are not inclusions. These are minute, atomic, and extended defects and impurities. These may be related to small holes, such as vacancies, or they could be nitrogen, boron, nickel, or silicon related. So there's a whole family of defects that are present in diamond. Now, defect, it's a bit of a troubling nomenclature. Defects aren't bad. That's just something other than the diamond lattice. Any type of imperfection is known as a defect. These defects, these impurities, can actually be the source of some fascinating and beautiful colors in diamonds. So for instance, you have boron that creates blue color in diamond, such as in the famous Hope diamond. Also, it can result in useful properties for uses outside of the gemological community. For instance, the same example, boron leads to electrical conductivity in diamond and means that it can be used for certain type of electronic applications. Now, the reason that we at GIA are very interested in defects in diamond is because by considering the presence, absence, relative concentrations, and their distributions in the diamonds, we're able to determine whether the diamond is natural, treated, or laboratory grown. So it tells us information about the diamond's origin. So what we'll be looking at today are these glowing diamonds, as I termed them. So really this glow is known as luminescence. So it means that when we subject the diamond to some form of electromagnetic radiation, it stimulates these different types of defects, and they're able to be excited into a higher orbit, as shown here. And then as they relax back to their stable form, when you say switch off the light, you get the emission of light. So this visible light comes out of the diamond. So this is the luminescent features that we're after. Luminescence can then be grouped into two different categories. We have fluorescence, which is the term that I believe most of you would be familiar with. And this is the response to illumination with UV light, ultraviolet light. Now, the UV fluorescence that is included in all diamond grading reports is a long-wave UV fluorescence. So we'll be going through different types of UV fluorescence in the next few slides. Another phenomenon that we're also very interested in is phosphorescence. This is the emission of light once the stimulating light has been turned off. So in the case of UV light, you would say illuminate your stone with a UV source, and then once you switch it off, it continues glowing. This is the phosphorescence effect. And here we have two different images that just really illustrate this fluorescence effect in diamond. We have this beautiful necklace by Harry Winston, where in white light, you can see that all these stones are just colorless diamonds. Whereas under UV light, so the black side of the image, you can see that all of these different diamonds are showing different types of blue fluorescence features. And then on the left-hand side of the image, we can see a range of colorless diamonds with different types of fluorescence intensities. So these are the fluorescence grades that we include in the GIA diamond reports. So we have the standard gem testing lamp, which can emit shortwave UV, which is at a wavelength of 254 nanometers. And then you also can switch over to longwave UV to 365 nanometers. So again, just repeating that when it comes to the fluorescence that's reported in the GIA grading reports, it would be that under longwave UV. And then it's also possible to use even shorter wavelengths. So this deep or ultra shortwave UV has a wavelength that is less than 225 nanometers. And the typical instrument that's used for imaging these stones under that emission is a diamond view. So this is very, very high energy UV. So it's very dangerous for our eyes, which is why it's done within an enclosed system. And the great thing with the deep UV illumination is that it excites fluorescence in practically all diamonds. So even stones that would have a characterization of non-fluorescent on a report would fluoresce under these conditions. Also, the images that you'd be able to collect are going to be very sharp and very surface specific. So you get very, very detailed images of these growth zones that we'll be going through. So we'll give you examples of responses to shortwave, longwave, and deep UV in the next few slides. The other luminescence tool that we use, which is mainly done in a gem lab or a scientific environment, would be cathodoluminescence. In this case, rather than using UV light to excite the defects, we use an electron beam. So this is, again, going to produce a very surface-specific illumination of the defects. And in this case, under the conditions that we use at GIA, usually the depth of what you're observing is going to be about 2 microns, so very, very, very small. This can be done using 2 different types of machines. So the luminoscope in the bottom is something that was used for cathodoluminescence imaging, where you're just looking through a small aperture at the top, shown here. Since then, most cathodoluminescence is instead conducted by having it as an attachment on a secondary electron microscope. The great thing with that is it gives you extremely high magnification. So we're talking about 20 to 30,000 times, depending on the setup. So it means that you're able to look at very, very fine features in the system. Now, one of the questions you may have is, how common is fluorescence? So we consider D to Z color diamonds in a study created by Tom Moses in 1997. He studied 26,010 diamonds that were coming through the lab. And out of those, they found that 35% of them fluoresced, whereas 65% were inert. And this is to long-wave UV. Out of the fluorescing diamonds, 38% had faint fluorescence, whereas 62% had medium to strong. Now, looking at that smaller group of, medium to strong diamonds, we saw that 97% of the stones fluoresced blue, whereas only 3% had some other fluorescence color, so orange, green, yellow, purple, etc. When it comes to fancy color diamonds, fluorescence is much more common. So here we have these 2 beautiful images where under white light we can see a section of the aurora butterfly of peace, and then on the right we can see the same stones, same configuration, under UV light, and you can see that they are glowing several different colors and very, very intensely. When we consider fluorescence, we need to consider the excitation wavelength. So certain defects, these impurities, these centers that we're looking for, are much more efficiently excited by certain wavelengths. Now, wavelength and energy are inversely proportional to each other, which is sort of illustrated by that diagram on the right. So long wave UV, which was 365 nanometers, has an energy of 3.40 electron volts. Shortwave gives you 4.8 electron volts, and then the ultra shortwave or deep UV is greater than 5.51 electron volts. So here we're just illustrating that the shorter the wavelength, the higher the energy of the excitation. Now the luminescence color that we observe depends on the concentrations of the emitting defects. So these diamonds don't just contain one single type of defect, they have a whole range of impurities in there that are going to be emitting light at the same time. Additionally, they can interact with each other. So a lot of people think of non-fluorescent diamond as being purer than fluorescing diamonds, but that's not necessarily the case. In fact, one of the defects that causes most of the fluorescence, which is the N3 defect, if you have another defect present that's an A center, which are nitrogen pairs, that nitrogen pair center is able to effectively steal the fluorescence, absorb the fluorescence of the N3 defect. So the diamond could have plenty of impurities in the stone, but we cannot observe the fluorescence. It's sort of stolen the fluorescence from them. What we observe is going to be a cumulative effect of all these different defects. If we want to observe and identify the specific components of the overall fluorescence, we need to use spectroscopic means. So that's something that we won't be discussing today, but it is possible to identify it. And one of the key things about luminescence color is that it can be changed through treatments. So because treatments change the types of defects that are present in stone, you will be able to change the luminescence color. Now, when it comes to pattern, the defect distribution is unique to the diamond. It's the fingerprint of the diamond. Every stone has its own unique configuration of defects. One of the neat things about the luminescence pattern is it cannot be removed by treatment. So this is something that is stable and will always indicate whether the stone was grown naturally or synthetically by humans. So we'll be looking at a lot of those patterns today. When it comes to the defects that are responsible for the fluorescence colors, here we have the three most commonly observed ones. So the N3 defect, which is 3 nitrogen atoms surrounding a vacancy. So again, remember, diamond is just a series of carbon atoms. So we replace some of those carbon atoms with nitrogens and a vacancy, which is just a small hole, an atomic hole. We get the N3 defect. That produces the blue fluorescence that we're all very familiar with. So the most common fluorescence observed, the 97% of D to Z color fluorescing diamonds, have this N3 fluorescence. Another color that you might observe would be green, which is usually associated with the presence of H3 defects. H3 defects have the atomic configuration of 2 nitrogen atoms surrounding the vacancy. And then you have the nitrogen vacancy defects that produce generally warm colors, oranges, reds, occasionally hot pink type colors. And that's again a nitrogen next to a vacancy. So as you can see, these are atomic defects in the lattice. And there are many more fluorescent defects. And for that, if you are interested in learning more about them, GIA scientists have produced a series of different articles on it. So for instance, there's a quick reference chart, which is shown here by Shigley and Breeding from 2013. And these 2 columns here are related to the long wave and diamond blue fluorescence colors. So it gives you a lot of information on the behavior that you might see if your diamond contains those defects. If you are interested in the lighting that you use, the UV lighting and its effect on exciting different types of defects in diamond, the article by Lua and Breeding is looking at the fluorescence produced by these optical defects and showing some of the spectra. And then finally, we have this article by Dr. Ita Naganya, who is then looking at the fluorescence spectra on a lot of these fancy colored diamonds. As I mentioned before, there is another phenomenon that we're also interested in, which is related to this, the phosphorescence. So this is when, after you have illuminated the sample with, for instance, UV light, the diamond continues to glow once you switch it off. And this is a really beautiful effect, in my opinion. Usually it is something that you observe in blue diamonds that are boron containing. And the phosphorescence that you might see might be either blue or red, depending on which relative defects are present in the material. So they're all boron related, but there are two different bands associated with it. One at 500 nanometers, which is the blue one, and then the red one at 660 nanometers. And these features decay at a slightly different speed, which is how you can end up with this image here on the right, which shows that after initially, when you switch off the light, you have blue phosphorescence, but as time goes on, the blue component disappears and you're just seeing the red component. So this type of phosphorescent effect has been studied very deeply by, again, Eaton Magana in these two articles from 2007 and 2011. And this image itself comes from Moe and Johnson in 2007. One of the most famous phosphorescing diamonds is going to be the Hope diamond, so US national treasure. And you can see here that is phosphorescing very, very intensely red. Other phosphorescence colors that you might observe are going to be yellow, very rare, but occasionally observed with chameleon diamonds. And one of the neat things with phosphorescence is that usually it decays after a few seconds. So it's not particularly long-lived. And this is something that will be very useful for us when we're looking at identifying and separating natural and man-made diamonds. So if we're going to look at patterns, we need to consider how the diamonds have formed. So when it comes to natural diamonds, most diamond crystals form at depths of approximately 150 to 200 kilometers below. That's sort of shown here. You can see this little keel here, where you have a lot of little diamonds, and that's at about 150 to 200 kilometers of depth, which translates to, say, 124 miles deep. And these diamonds have formed extremely long times ago, 650 million years to over 3 billion years ago. And as these diamonds are forming, they are incorporating impurities and defects from their environment around them. And these give us a good indication of the formation processes. And that's one of the reasons that geologists are particularly interested in analyzing defects in diamond. It gives us a lot of information about how the earth has formed and how things are happening underneath the surface. So most diamonds, when they grow, they form an octahedral crystal shape. So it's effectively two pyramids stuck, square-based pyramids stuck against each other, as you can see here. Now, although some of these nice, beautiful octahedral diamonds can be found, most diamonds have actually gone through a process of resorption. So the fluids that the diamonds are in the mantle or during its transportation in the kimberlite can etch the diamond. So you will see that as the resorption is occurring, it's sort of etching out all the edges until eventually you end up with a dodecahedral shape. So these are some of the most commonly observed crystal structures that are seen for natural diamonds. So we had this beautiful octahedral diamond, and were to say slice through it, we would look at the interior growth structure. And here you can see squares and a series of little sort of wavy patterns. This is the octahedral growth pattern within the stone. So these are the tree rings, the fingerprint of the diamond. And you know, this is an idealized cartoon, but really it can be very applicable to the patterns that we observe in natural stones. As shown here, they are effectively a fingerprint over the diamond. It's a very unique pattern for each individual stone. Yet you can see that these two stones, this 1.18 carat and 1.24 carat diamonds, have this princess cut, they both look pretty much the same. In fact, they are mirror images from each other. And that's because they were cut from the same rough diamond. So these are two diamonds that were submitted separately at GIA that we were able to link because of their unique growth patterns. And you can see that these patterns look very, very similar to the idealized cartoon version. And this is the octahedral growth pattern that is natural. A way to think about these patterns is to think of them as tree rings. If you have a tree and you were to chop it down and look at the tree trunk, you would see a range of different rings that are showing changes in the seasons and the environment as it was growing. Diamonds have the same thing. So here you can see this pattern in this natural diamond. This is using the diamond view instrument, so deep UV fluorescence. It's glowing the sort of greenish yellow color, which tells us that there are H3 defects in the material. And these patterns can be quite complicated. It almost looks like malachite. Here you have another standard natural diamond, in this case showing the much more common blue fluorescence color for the nitrogen of the N3 defects, or 3 nitrogen surrounding the vacancy. And you can have combinations thereof. So there are very many different fluorescence colors, but really here we're focusing on the patterns. Using photoluminescence, we can again observe these patterns. In this case, it's just a black and white image, but we can very clearly see different growth features, such as this twin plane. And if we look at the magnification here, this is 100 microns, so very, very high magnification. These are very small stones. There are other patterns that we can observe as well, much more rarely. So some Zimbabwe diamonds, which typically have this sort of green, olivey, browny type color, can show very rare cube octahedral shapes. So it's a combination of the octahedral shape and a cubic growth habit. So usually what you end up seeing is something that looks like a little bit like a cross, or maybe something more flowery. And not just these minute atomic impurities are incorporated differently in the different growth zones, but you also have clouds that incorporate differently. So in this case here, we have a slice through a diamond, and we can see these sort of brownish features, and these are just small, minute clouds that have formed this pattern in stone. And you can see that also quite clearly here. These reflective speckles are just clouds that are being reflected off it. Now, the diamonds that I've been showing you previously were diamonds that have a lot of impurities, a lot of nitrogen-related features usually. How about very high purity stones? Well, natural type 2 diamonds, so these are the diamonds that show very low nitrogen concentrations and are oftentimes extremely valuable, do not show growth zones generally. Instead, what you're most likely going to see these web-like mosaic polygonized dislocation patterns. And this is because a lot of these stones have suffered from a lot of plastic deformation in their time in the earth. And it creates a lot of dislocations, which are sort of small lattice imperfections that can, at the temperatures of a formation, move around, find each other, and link up, and effectively create this web-like pattern through the stone. Defects associated with these dislocations can give a very clear blue, violety blue fluorescence. It's unknown exactly what the defects are, but they're just termed band A fluorescence. And sometimes you will see the patterns overlaying on other much more intensely fluorescent defects. So for instance, here you can see the dislocation network is dark, and it's on top of this sort of background green fluorescence from the H3 defects that are present in this particular stone. So these are very, very natural patterns that we have been observing in the last few slides. And try to keep those in mind when we start looking at man-made diamonds. So if we were to look at those patterns again under higher magnification using cathodoluminescence, where we're using an electron beam to excite the defects instead, we can see that some stones that appear to have no very clear patterns under magnification again are showing these very nice dislocation patterns, these polygonized dislocation patterns. And here, these little spots that we're seeing, these little flecks, are actually more concentrated dislocations within the material. So it can really reveal some of these hidden patterns. And the patterns in natural diamonds can be absolutely beautiful. So here we have a fancy deep brownish orangey yellow diamond. It's about 0.5 carats in size, SI1 clarity. A nice stone, wouldn't you say? However, when you look at it under UV, you see something much more fascinating, at least in my opinion. We see this extremely complicated pattern here where there's a little bit of growth zoning. So we can see these growth zones going through here. Then there's a lot of flecks and just lots and lots of different impurities that are fluorescing very strongly. And it gives us this sort of galactic rainbow effect. And the people who found it here at GIA, Christopher Vidrell and Tyler, they actually decided that this looks a little bit like a howling spirit wolf. So this really shows how these fluorescence patterns can actually bring a little bit of romance to the stone as well. Now moving on to lab-grown diamonds. So these are, chemically speaking, the same crystallographic structure as a natural diamond. So again, it's carbon atoms in a tetrahedral arrangement as shown here on the right. The only difference is that these are grown by humans in a laboratory setting. There are two main growth techniques: the high pressure, high temperature method, which is effectively where they're trying to compress and form diamond from some other carbon source, such as graphite, at high temperatures and pressures, or the chemical vapor deposition method, CVD, which is instead a gas phase chemical reaction that they're doing in order to convert, again, gaseous carbon sources into diamond. And we'll be going through these two different methods in greater detail. For HPHT diamond growth, they use a press. So this is the same type of press that some people use for diamond treatments. So it's an HPHT press that is going to try to mimic some of the key conditions of natural diamond formation. The pressures are going to be about 5 to 6 gigapascals, which is again equivalent to the types of depths that natural diamonds form at. The temperatures are about 13 to 1600 degrees Celsius, and the duration of this growth is going to be days to weeks long, depending on the type of material that they're trying to grow and the sizes. So here you have this little cartoon of sort of the inside of an HPHT capsule. And the key ingredients that they have are, they have to start with a piece of diamond, the seed crystal. This could just be a small piece of diamond, say from diamond grit that they produce for the grit and polishing industry. So just a small sacrificial seed crystal that is going to act as the template for growth. And then what they do is inside of this capsule, which you can think of as being sort of the size of a can, a soup can. Inside of this capsule, they're going to have some sort of a carbon source, which is generally going to be graphite, but potentially also diamond powder. And they mix this with a series of metal solvent catalysts. And these are going to be generally ferrous in nature. So there's going to be iron, and then they might have some other alloys in there, so nickel or cobalt. What they do then is they turn up the temperature, and they produce a temperature gradient so that the region close to the carbon source is hotter than the region close to the seed. What happens is that these carbon atoms are going to dissolve into the melted metal, and then they're going to work their way down towards the cooler region with the seed, and then recrystallize a synthetic diamond, so man-made diamond, on these much cooler seeds. And then depending on how they're doing their growth, they could have one or several crystals growing at the same time. And what you can see here is your little small seed crystal, and on top of that, this sort of large crystal that has grown out of it, this orange crystal. And that's the HPHT diamond. So that's the new diamond material that was synthesized. And that structure that that diamond has is known as a cube octahedral shape. So an octahedron, again, was going to be this square-shaped pyramid, two pyramids stuck to each other. So you have this sort of pyramid shape, and then you just sort of shave off the corners, which is the cubic shape to it. So this is the cube octahedral structure. Now these diamonds, when they're growing along different crystallographic directions, it's illustrated here, at different growth rates. And that's going to create these growth zones going through there, these growth sectors. So for instance, this orange sector here was all grown with growth along this direction. And the uptake of impurities is going to differ for these different growth directions. So these different growth sectors are going to have different impurity concentrations. If we take this HPHT diamond and were to slice through it at point A or B, you get this pattern here. So that's really showing you all those little growth sectors. And the different colors here represent different concentrations of the defects. And you can clearly see that there's sort of a square shape with a cross going through it. So this is sort of termed the Maltese cross. So anything that looks like a cross or potentially an hourglass would be something that is fairly common in HPHT diamond structures and rare in nature. So we'll be showing a lot of examples of that. So using a standard long wave UV lamp on fancy colored HPHT synthetics, you might actually be able to reveal this cube octahedral pattern just by the relative intensities of the defects. As I said, here the defect that produces green fluorescence is very intense in certain zones and much less intense in other zones, so you can clearly see this cross shape going through. And this is something that you wouldn't be seeing in natural diamonds. If we consider instead colorless diamonds, when we consider the natural colorless diamonds, just as a recap, 35% of them are going to fluoresce through long wave UV. Out of those, the most common color is going to be blue due to the N3 defect and potentially a little bit of band A. And the response that we see to long wave and short wave is that long wave UV creates stronger fluorescence than short wave UV. Now, when it comes to HPHT diamonds that are colorless, in this case, colorless really means more sort of D to Z type colors, so the full non-fancy color range. The long wave UV is going to cause yellow-orange fluorescence. To short wave UV, you will also see yellow or yellow-orange fluorescence and intense green-blue phosphorescence. Now, this phosphorescence, as I mentioned before, is extremely rare in natural diamonds, so it's going to be something very good as an indicator, and we'll come back to that soon. One of the key features is that not only is the color different to what we usually observe for the fluorescence of natural diamonds, but also the intensities are inverted. So in this case, the short wave is the one that is producing a stronger response than the long wave UV. Again, very rare for natural diamonds, so a good indicator that the stone needs to be inspected more carefully. When using deep UV fluorescence, we're able to see the patterns because these stones don't have a very clear pattern when observed using either long wave or short wave. With the deep UV, we're able to see these very beautiful cube octahedral patterns that are indicative of their man-made origin. And sometimes the patterns are much more easily observed when looking at the stone through the pavilion. Again, these stones are going to have very, very strong, intense, long-lived phosphorescence, which is going to help us flag these stones as potentially synthetic. And by long-lived, I mean very long-lived. Some of them can fluoresce for several minutes, whereas natural diamonds are going to fluoresce for a matter of seconds. So this is very, very rare and very neat phenomenon. So these patterns have to do with the relative concentrations of the defects in the different growth sectors. So for a colorless stone, you might assume that it's going to have a lower concentration of defects. And when it comes to HPHT synthetic diamonds, man-made diamonds, that is true. So I'm not sure how easily you can see these patterns here, so I'm just going to accentuate them, but you can see again the square and the cross going through them. And then from the side, you can again see these very geometric patterns, very sharp edges, quite different to what we're observing for natural stones. And this is a very high purity stone. So this would be a type 2 diamond, which if you were looking at a natural type 2 diamond, you would be expecting to see blue fluorescence patterns and that they would be these dislocation networks, this web-like pattern. So again, very different to what we observe in natural stones. So it immediately tells us that this is man-made diamond. When we look at fancy colored HPHT diamonds, you're going to have a range of different types of impurities, which are causing the color. And that also means that you're going to have a wider variety of fluorescence colors. But again, one of the useful things to us is that typically the short wave UV is going to be stronger than the long wave UV response, which is opposite to what we observe for natural diamonds. And for fancy colored diamonds, it's much more easy to observe these growth patterns. So again, you can see the crosses going through all of these different examples. And coming back to the phosphorescence is actually something that has been used a lot for the identification of HPHT synthetic diamonds for melee goods. So as I'm sure a lot of you are aware, there's a lot of concern in the industry about the mixing of HPHT synthetic diamonds that are being mass produced in China with the natural melee goods, partly because a lot of those goods don't go through rigorous testing at laboratories. So one of the ways that people have tried to flag diamonds that might be potentially HPHT synthetic is by illuminating them with UV light and looking for a phosphorescence response. Very rare for natural diamonds, extremely common for HPHT synthetic diamonds. So here we have the responses, the phosphorescence responses to long wave and short wave UV for two different Chinese producers. You can see that the short wave UV gives you a much stronger response, but occasionally you can also see something with the long wave UV. Now, this is great. It means that there's actually a lot of instruments on the market that are used for identification that are based on this phosphorescence response. But one of the things to keep in mind is that can be prevented. So there was in 2018, there was a press release that came out of Hong Kong that was saying that it is possible to kill the phosphorescence of the HPHT synthetic diamonds, so the man-made diamonds. And that's just through a very simple irradiation treatment. Now, it's something that we haven't seen frequently, but just to make it very abundantly clear, all the GIA identification devices that we have for the trade are not based on phosphorescence due to this. Ours are actually based on different types of methods. So even if a diamond had been treated that was man-made, to get rid of the phosphorescence, our systems would still be able to confidently refer them as potentially synthetic. So they can't go through the cracks using our instruments. The other method for growing diamonds is chemical vapor deposition method, so CVD. Now this is a totally different method. It's based on gas phase chemical reactions. So you can think of it as being sort of a very, very fancy microwave oven. So what we have here on the left is going to be our CVD reactor, and inside it there's going to be a series of little crystals. So these are known as substrates. These are pieces of diamond. In the same way that for HPHT synthesis you needed to have a small piece of diamond to get the growth started, you need to do that for CVD as well. In this case, the source of the carbon for the growth is going to be a hydrocarbon gas, usually methane, in an abundance of hydrogen. And that sort of goes into the system, and they're working at very, very low pressure, so a fraction of atmospheric pressure. And the temperatures are about 700 to 1,000 degrees Celsius. And the duration of growth is going to be a matter of days to weeks. So what they do is they flow these gases through, and then they activate them by some energy source. It could be a filament, or more commonly, a microwave. So this is why I think of it almost like a microwave oven. What happens then is these different gaseous molecules react with each other. You create this plasma. So it sort of looks like a light bulb. It actually glows. And these molecules are then able to react with the diamond substrates and effectively photocopy the structure beneath them. So you get layer by layer growth. Atom by atom, you get new diamond growing upwards. Depending on the impurities in the system, for instance, if they introduce certain chemicals, or if they do some sort of treatment afterwards, you can have the full range of diamond colors as well. So here we have a little cartoon of that. So this is the inside of a CVD reactor. And here you can see all these little pink glowing plates. So these are the diamond substrates. And on top of that, you have the plasma. So diamond growth is occurring here. Now these particular plates, they look pink right now. That's not because they actually are pink. It's not fluorescence either. Actually, this is the stones are very, very hot. So they're glowing in the same way that if you take a iron poker and put it into the fire, it might glow. So this is the same type of effect. So here you have your diamond lattice, and then on top of that, the gaseous species, and slowly but surely, atom by atom, you get new CVD material. When we consider CVD diamonds, the fluorescence behavior is not quite as helpful. So near colorless diamonds, the vast majority of them are not going to be fluorescing to long wave UV light. So they're going to be inert. So with a long wave UV light, you wouldn't be seeing anything that, for the vast majority, you wouldn't see anything that would alert you that they might be synthetic. However, from the subset that do show some sort of fluorescence, the most common colors that you're going to see are going to be orange, yellow, or green. Again, thinking back to natural diamonds, 97% of the fluorescing natural diamonds show blue fluorescence. So these colors are going to alert you that you need to be careful. For the pink CVD diamonds, so it's a very common, popular color in the trade, you're going to see a lot more fluorescence, and those are going to show red, orange, or yellow fluorescence. So again, rare colors, and something that alerts you that you might be dealing with a man-made material. So using deep UV fluorescence, we're able to get a lot more information. So for the CVD synthetic diamonds, so the man-made diamonds, there are certain treatments that are used to change their appearance. HPHT processing, which is when you heat a diamond in a HPHT press, can be used to decolorize certain stones. So a lot of CVD diamonds, when they're grown, they originally have this quite unappealing brownish tinge to them. And by HPHT processing, they're able to remove the defects responsible for that brown color and end up with a much more valuable colorless material. It's similar to the HPHT processing or HPHT treatment that exists for some natural diamonds as well. When we consider the as-grown CVD material, the most common colors are going to be orange, pink, or reds, and that is because these diamonds contain a lot of nitrogen vacancy centers. So that's the defect here on the top. These stones rarely show phosphorescence, but the UV fluorescence color is rare enough to alert you that you need to be careful. When it comes to the HPHT process, so the decolorized CVD diamonds, this is going to change the relative concentrations of the defects, and instead now the fluorescence is going to be green to greeny blue. And that's because H3 defects, so the 2 nitrogen vacancy centers, and the N3 defects, which are 3 nitrogen vacancy centers, are produced by this treatment, and they glow green and blue respectively. Additionally, these stones will show greenish blue phosphorescence, a rare feature in diamonds that again alerts you that you need to be a little more careful. Now, as I mentioned before, one of the good things about UV imaging is that the patterns are intrinsic to the stone and they cannot be changed by treatment. So here we have some deep UV fluorescence images for as-grown and HPHT process CVD diamonds. And we'll be going through the features and how they form in the next few slides. But one of the immediate things that you can see is that the as-grown show these warm colors, a lot of these reds and pinks, whereas the HPHT process stones are showing these cooler colors. These are these blue, greeny, aqua type colors, a little bit of green, and they also show phosphorescence. And if we think back to what standard natural diamond would look like, you would instead be seeing blue fluorescence most commonly. And this polygonized dislocation pattern for the diamonds that are high purity. Now let's consider these growth patterns and how they form. As I mentioned before, the CVD diamond is deposited ideally by step flow growth. So pretty much you get a layer and it sort of flows across the surface of the diamond, and atom by atom you get the next layer onwards. So effectively what you have is a series of steps on the surface of the diamond. So here we have this cartoon, we have the substrate, in this case I show as green, and then on top of that you have a series of steps and terraces. And these different terraces and risers are presenting a different crystallographic direction to the gaseous species above. And really all that really matters about that is that certain defects are going to prefer to go into the terraces, whereas others will prefer going into the risers. And this means that if you have something that has grown quite thickly, from the side, you might eventually form a series of very tightly spaced lines, shown here in orange, that are known as striations. Now, clusters of lines in a diamond are really quite rare in natural diamonds, so anything that shows a series of lines is going to be concerning. So here we have an example of an as-grown CVD grown diamond that is showing this very clear orange fluorescence due to the nitrogen vacancy centers. And if we zoom into that section here, you can see a series of very tightly spaced lines, these striations. Now, CVD diamonds could be grown in a single step or multiple steps. So what we have here is uninterrupted growth. So you have your substrate and the striations forming diagonally. But you could also grow it as a series of steps. So pause, repolish, for instance, or change your conditions in your growth system, and then continue growing. These interruptions are going to change the concentration of the defects very, very clearly, as shown here. So this is a cross-section of a CVD diamond, and we can see at the bottom we have the substrate that is fluorescing green, and then on top of that we have the CVD layer. We have an interruption that is causing a very clear line going through the material, and then these diagonal striations. You can also observe this sort of wispy blue fluorescence pattern, and that is coming from dislocation networks, so small atomic imperfections of the lattice. So here we have an example of a large 3.26 carat CVD diamond that was obviously grown using a series of layers. Again, we have the layers, and we can see the striations diagonally. And this can actually allow us to figure out how the diamond was grown and how it was cut out of the original cube of CVD material. And then if we use higher magnification, such as the cathodoluminescence technique, then we'd be able to see these striations much more clearly. So really, these techniques are able to show us a lot of the features that are intrinsic to the stone that make them unique and allow us to separate the natural from the lab-grown material. As a just quick recap, the fluorescence colors are related to the excitation wavelength. So whether you're using long, short, or deep UV light, and the type of defects that are present. And then the patterns for natural diamonds, we'd be expecting to see something like tree rings or potentially dislocation networks. For the HPHT grown diamonds, we'd be expecting to see cuboctahedral patterns. And then for the CVD grown diamonds, we can see striations and layers. And then using cathodoluminescence techniques, we can provide much better contrast and resolution. So thank you very much. I'd love to hear any questions that you may have.
Okay, that was great. Thank you. So this question came in on one of your more recent slides. So I'm going to ask this one first.
Okay.
It was around slide 45, and you were talking about magnification. What level of magnification do you need to use? I think it was right around the CVD growth pattern slide.
So as a frame of reference, here you can see the sizes of these stones. So really this magnification is just of the order of sort of 20 times or something along those lines for the diamond view instrument. So you can oftentimes observe the patterns using that type of magnification. But the thing is that here we're using very intense high energy UV, which is dangerous to the eye. So you can't do it, say, using a microscope and a UV light. This has to be done using a specialized enclosed instrument, unfortunately.
Okay. Are the striations in CVD diamonds similar or different to curved striae in synthetic flame fusion ruby?
I'm afraid I don't work with colored stones.
We'll
so
defer that.
Sure
we'll ask. Yeah.
Yeah, sorry, I'm not sure. I'm afraid I can't answer that. But we're looking for very tightly spaced lines going through the material.
Okay. There were a lot of questions around fluorescence and how that affects the appearance.
Okay.
So can you talk a little bit about how fluorescence may affect the appearance of a diamond and you know, any known percentages we have of, you know, the impact and maybe like the level of impact it has on the appearance of the diamond?
So for that, I'd refer viewers to the paper by Tom Moses in Jensen Gemology in 1997. So that will really go through and give you all the little pie charts for it. But really what they found is that although the trade has this perception that fluorescence is potentially a negative thing for the stone, they found that when viewing the stones table down, the fluorescence had no effect on the appearance. Now, the reason that's important is because that's the setup that is used for color grading diamonds. Yet, when viewed table up, as you would have in, say, a mounted piece of jewelry, they did see that the fluorescence could actually improve the appearance of certain stones. So this was most noticeable for I and K type colors. So the
Okay.
fluorescence can actually make the stone look better. And then there are certain diamonds that show very strong fluorescence that you can even observe in regular daylight conditions. And those can be, some people really like them, some people don't like them, and link it to a milky appearance. Yeah, very, very unique stones in my opinion.
Yeah, and all the G&G articles that we have going back to the 80s are available on GIA's website, so you can find that article in full at
Exactly.
gia.edu.
Yes, all the articles that I have been referring to today are available on the Jensen Gemology website, and they're all free for everyone.
Yes. How closely related are luminescence and beta radiation? And can we get a luminescence material to emit beta radiation?
There are two very different effects. I'm not sure I'd be able to explain that here, but a luminescing diamond and beta radiation are two totally separate things. One of them is that a material is emitting particles versus what we're now emitting light. So it's two totally different phenomena.
Okay. Can we differentiate between CVD using some of the techniques that you talked about today? So can we use just an understanding of, you know, of phosphorescence or photoluminescence, or can we use that as a to determine if it's CVD with confidence?
Yes, so for some of the examples that I showed today, for instance, the one that's up right now, you would immediately be able to tell that this is a CVD diamond. So again, we're looking for these layers and these striations combined with, say, the colors that we're observing that would be extremely rare in nature. That would allow us to identify these conclusively as CVD. In fact, usually these patterns are, amongst all the different testing techniques that we use, these patterns are finally the key thing that we use for the conclusion.
Okay, great. Well, you know, that covers most of it. So we're just about running out of time. So thank you everyone for joining us today. Thank you so much, Ulrika, for taking the time to walk us through all of this. If anybody has any questions, please find us on Instagram, Facebook, LinkedIn, and Twitter. Thanks again, and join us next week where Akira Hyatt will be here to break down the GIA 7 Pearl value factors, and we'll get a sneak peek of the new cultured pearl and classification report.